Okay, this is 8.9, part 1. I'll now do a proof of problem 2, the one about palindromes. Okay. All right, this is not something you're required to do for this homework assignment. This is just a lecture. It gives you a good idea of what you got to do for problem 3. Okay, write our initial case is lambda 0 and 1 are in S. Recursive rule is that if X is in S, recursive rule 1 tells us that 0x0 is in S. Recursive rule 2 tells us that 1x1 is in S. Okay, so now the property that we're going to try and prove is P of X. X is a palindrome. Okay, base case. Base case, we're going to prove that X is a palindrome for each of the things in the initial case, lambda, 0, and 1. All right, so this I think is rather clear. We can just see that clearly lambda, 0, 1 are the same when read forward or backward. Okay, that's the proof of the base case. There's not much to say, right? What is a palindrome? Right at the top of the page, a palindrome is a string that is the same when read both forwards and backwards. The empty string, there's nothing there, right? So if you read it forward and backwards, there's always nothing there. So it's always the same. Same thing with just one thing. There's only, okay, so now inductive step. So here we're going to assume P of X is true for some X and S. All right. So we have X, and now X, recursive rule 1 will do something to X, recursive rule 2 will do something to X. So we got to treat both cases separately. So you can think of this as a proof by cases. You can just say recursive rule 1. Y is equal to 0, x, 0. And our goal here is to prove P of Y, that Y is a palindrome. Okay. All right, so now we just need to explain why 0x0 must be able to be read, must be the same when read both forward and backwards. Okay, let's see, X is a palindrome, so X is the same when read both forward and backwards. So all right, so maybe we say something like reading Y forwards. You start with a 0, then you read X, and then you have a 0 at the end, right? Starting, so let's say reading Y from the left, or let's say reading Y forwards. reading y forwards, we read 0, then whatever x is, then end with a 0. Reading y backwards, we read 0, then whatever x is, then end with a 0. Okay, so here's, all right, so I know it seems obvious, and it is basically obvious, but still, it is a good exercise to really see why it's obvious. If something's obvious, then you should be able to explain why it's true. And here I am explaining why it's true. I think I'm capturing the essence of why this is true. Okay, and it is in the fact that we're using induction here. We're assuming the thing that came before x is a palindrome. So it can be read the same forward and backwards. All right, so when you read y, which is recursive rule 1 applied to x, forwards, you read a 0, then whatever x is, then a 0. When you read it backwards, you read 0, then whatever x is, and then 0. Okay, now the key point here is the induction, right? The key point is the fact that x is a palindrome, so x can be read the same forwards and backwards. So since x is the same, okay, I messed that up a little bit. Since x, let me write this. Since x is a palindrome, right? So let's see, since x is a palindrome, since x is the same, when read forwards and backwards. Since x is the same when read forwards and backwards, since x is the same when read forwards and backwards, and when reading y, we start and end with the same thing. The same thing, 0, in this case, y is a palindrome. Okay. All right, so that's recursive rule 1. All right, now recursive rule 2. Almost exactly the same proof, right? Recursive rule 2, so I'm going to take out all these zeros here. Okay, and I can replace those. I'm going to replace them in red to emphasize that I'm doing something different. To 1x1. Reading y forwards, we read 1. Then whatever x is, then we end with a 1. Reading y backwards, we read a 1. Then whatever x is, then end with a 1. Okay. Since x is the same, we read both forwards and backwards, and we start with a 1 and end with a 1, then this will be the same forward and backwards, right? That's the idea. All right, so that is a proof by structural induction.